If your classifier looks 90% accurate, but still fails on the rare important cases, accuracy is lying to you. We will plot ROC and precision recall curves in Python so you can see threshold trade-offs instead of trusting a single number. You might be debugging a fraud detector or a medical screen. Most events are negative, and a single accuracy number hides misses on the rare positives. By the end, you will read model scores, rank candidates, compute ROC AUC, and pick thresholds that meet precision or F1 goals. That gives you control instead of blind trust. I'm Professor Pi, teaching AI foundations from basics to advanced with simple, concepts-first Python that helps you solve bigger real-world problems. Think of a simple alerting pipeline. A model assigns a score to every item. We decide a threshold and then act. The pain point is that default thresholds often miss the rare positives you actually care about. ROC and precision recall analysis let you inspect all possible thresholds and pick the one that matches your risk posture. At a high level, ROC AUC measures separability of scores without committing to a threshold. Precision recall tracks the trade-off that matters when positives are rare. Both are tools to answer one question: how well does the score order help me find the scarce true positives? We will build a tiny toy dataset with stable IDs and fixed scores. Then we will compute a rank-based ROC AUC. Next, we will look at top-ranked items, then pick a precision-driven threshold, and finally, pick a threshold that optimizes F1. That sequence maps directly to alerting and retrieval systems, so the code feels familiar when you scale it up. This snippet builds an imbalanced toy set and shows misleading accuracy. The list Y encodes rare positives at a few indices, while S holds fixed model scores for the same items. The IDS list gives stable identifiers so later ranking is easy. We apply a naive 0.5 threshold to S to get Q, then compute accuracy AC as the fraction of matches with Y. Accuracy can look fine here, even though 2 of 3 positives are missed due to the default threshold. The printed AC reveals how a single threshold can hide failures on rare cases. Next, we will compute a threshold-free separability metric. This example computes ROC AUC from ranks to judge score separability. The list SP pairs each score with its label and sorts by score, so higher ranks mean larger scores. We count positives N1 and negatives N0, then sum positive ranks into SR. The closed form AUC uses the rank sum to estimate the chance a random positive outranks a random negative. This avoids any threshold and looks only at ordering quality. The printed ROC AUC shows how well scores separate classes regardless of cutoff. If the value is near 1, the order is nearly perfect. If it is near 0.5, scores are no better than random. Now we will inspect the actual ranking the model produces. This code ranks examples by score and surfaces the top candidates. The variable ordIDX holds item indices sorted by the scores S from highest to lowest. The variable K controls how many to inspect, and top 3 slices the top-ranked subset. This ranking step mirrors how many retrieval and alerting systems operate before thresholding. Increasing K inspects more candidates and usually lowers precision, while decreasing K tightens focus. The printed top 3 shows which items your model would review first, and the IDs let you map those positions back to real examples or logs. Next, we will pick a threshold that enforces a precision goal. This snippet finds the lowest threshold needing a precision target. Using the ranked indices ordIDX, hits reorders labels, so positives arrive earlier if the model is good. The list tracks how many positives appear within each top K prefix. We collect all K, where precision over K meets pmin. Then choose the largest such K and take its score as THR to maximize recall under the target. Raising P-min pushes thrup and reduces recall. Lowering P-min relaxes free and raises recall. The printed threg shows the cutoff that achieves your precision goal and gives a concrete score you can use in production. Now we will select a decision rule that balances precision and recall. This snippet selects an F1 optimizing threshold from precision recall tradeoffs. We reuse CUM to compute precision and recall for every top K operating point. The list F1S holds the harmonic means of precision and recall, emphasizing balance for rare positives. Taking the maximum over all prefixes gives a practical decision rule tied to your actual objective. This makes a tiny but complete baseline. Pick K and its score cutoff where F1 is highest. The printed F1 summarizes the best achievable balance for this score. To map this toy flow to a real project, treat scores as your model outputs, IDs as sample identifiers, and the chosen threshold as the production cutoff. Use ROC AUC to check whether retraining or new features improve separability. Use precision targets when false positives are costly. Use F1 when you need a balanced operating point. Recap in 3 points. What it is. ROC measures score ordering, and precision recall shows threshold trade-off when positives are rare. When to use it. Inspect these curves whenever class imbalance makes accuracy misleading. One caveat, ROC can hide poor precision at low prevalence, so always examine precision recall too. Next step, scale this exact pipeline by running it on a larger validation set and log timing. Then track ROC AUC and precision at key thresholds over time. If you need a concrete knob, tune the threshold to hit the precision you actually require in production. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.